This is a summary of my final project on planning prehensile pushing in the horizontal plane using rapidly expanding random trees and motion cones. Pushing is a deceptively complex task, and I chose to focus on a simplified case, pushing a predefined object in a horizontal plane with a point contact, i.e. pushing an object while it rests on the ground. We can split this task into two main steps: developing a friction-aware planner that can find a series of feasible pushes that move a square block from its initial position to some desired goal, and implementing this trajectory on a simulated robot in order to evaluate performance. We limit the positions around the edge of a block at which a push can be applied to it. As we learned in class, a pusher at each of these locations can exert a force on the block that lies within a friction cone, determined by the coefficient of friction between the pusher and the block. If the pusher attempts to apply a force on the boundary of this cone, then it will slip. Motion cones can be viewed as an extension of friction cones. We use them to represent the set of possible twists that can be induced on an object by an external wrench. This diagram shows the general process for determining the motion cones for our particular task. In the case of pushing in the horizontal plane, the motion cone is composed of two wrenches, one from the pusher and one from the supporting surface, i.e. the ground. The pusher wrench can be found by transforming the set of feasible pushes to the block's own coordinate frame. The set of possible support wrenches can then be represented by an ellipsoidal approximation of a limit surface. The limit surface can be visualized as the capability of the ground to resist loads applied to the object. This is itself a product of friction between the ground and the object. In this video, we can see that the roll of tape doesn't move until the load being applied exceeds some threshold. This is indication of a support wrench resisting our efforts to move it. Once we have a set of possible pusher and support wrenches, we can combine them to find the direction of possible motions. In order for our block to move, we must apply a pusher wrench that respects the friction constraints, and this pusher wrench must be sufficient to overcome the corresponding support wrench. We can find the motions that result from this process through the vectors perpendicular to the limit surface at the locations where the pusher wrench intersects. The set of all of these possible vectors forms a motion cone, which we can finally represent in the world frame. Using motion cones to validate potential pushes, I successfully implemented a simple RRT planner. Note that due to the stochastic nature of this approach, there are occasions when the planner fails to find a valid path towards the goal. I introduced an acceptable tolerance of misalignment with the goal in order to improve the chances of finding a feasible trajectory. Trying to follow the planned trajectories in the simulator led to promising results. Due to the feed-forward nature of our controller, we observe an accumulation of error for longer trajectories. These errors result from inaccurate pusher positions relative to the block. Point contact pushing in particular suffers from instabilities. Small errors in position lead to unplanned moments on the block, causing steadily larger errors as the trajectory unfolds. Our planner also has no concept of an efficient path, instead simply returning the first feasible trajectory that it finds. This can lead to cases such as that on the left, where the pusher repeatedly alternates between different locations. This is in contrast to the more desirable trajectory on the right. Curved paths were found to be especially challenging. This is due to mistaken assumptions regarding our motion cones. Each cone is calculated for a particular configuration and is only valid for that moment along the trajectory. Since our planner operates in discrete steps, we do not verify that the friction constraints are maintained throughout the entire continuous trajectory. While this is acceptable during straight paths, we encounter issues when the applied pusher force is close to the motion cone's boundary, as in the case of a curved trajectory. Given the challenges we've explored, there are a few ways that we can improve the performance of our current method. If anyone is interested, a link to my final code is available in my report.